I'd like to talk about some mental schemes that we use in physics when we think about the connection between micro world, microscopic phenomena, and macroscopic phenomena. So not all parts of physics are preoccupied with this connection, but some parts definitely are concerned with it. In particular, particle physics, condensed matter physics, statistical physics are definitely interested in this connection. And there are two ways to think about it: the traditional way, which is what I would call reductionism, and I'll describe it, and then I'll describe a more recent way to think about it called Bootstrap. In fact, it's not a new idea. It's a rather old idea, but only in the last 10 years or so it started to fully realize its potential. So that's going to be the goal of my talk. So it's kind of an implicit assumption in physics that when we observe a phenomenon or some law of physics, we observe it at some distance scale, L, which is determined by the resolution of our experimental apparatus. But after we observe the phenomenon, we look for an explanation of this phenomenon, and implicitly, we always look for the explanation. We think that the origin of this phenomenon must be hidden at some smaller microscopic scale A, much smaller than L. So when we say in physics that we understand a phenomenon, it typically means that we manage to identify its microscopic origin, so some sort of microscopic model. And the funny thing is that you don't always need this microscopic model to actually do physics, to actually do computations at the distance scale L. But unless we have this microscopic model, many people feel uncomfortable. They think, okay, there is something that we don't quite understand. You know, it's a bit, it's in textbooks. You know, we learn it with our mother's milk. And you know, Lord Kelvin, in fact, in 1904, he said that we only understand a physical phenomenon once we have a mechanical model of it. Okay, he said mechanical model, but nowadays we say microscopic model. And so what do we mean by this microscopic model? Let me give a couple of examples. So one example comes from condensed matter, from the physics of magnets. So we think, or maybe know, that the origin of magnetism, the origin of magnets, comes from, at the microscopic level, from individual spins, magnetic moments of electrons, which are sitting at atomic sites of atoms from which our crystal magnet is made. And so that's an example of a microscopic model of a macroscopic phenomenon, magnetism. So particle physics offers a slightly different perspective on this connection, because in particle physics we have particles, and particles are themselves rather tiny entities. You can say that they are already kind of microscopic. But we are not satisfied with how microscopic they are. We build accelerators to smash those particles against each other, like, for example, now at LHC, at CERN, we smash protons. And when we do this, some other particles come out of these collisions. And we would like to understand why some particles are transformed in other particles. And typically, we think that the origin of this transformation is some sort of interactions between particles, and these interactions, they have their origin at some high energy, which means smaller distance scale, more microscopic distance scale. Also particle physics, it gives a good possibility to illustrate this concept of elementary phenomena, or elementary particles, as we say in particle physics. So always we kind of, at some point we stop. So we try to look for this explanation of what we observe at a smaller and smaller energy. But then there are, at some point we say, okay, we are comfortable that there are some phenomena or some particle that we will just accept them as elementary, and we will not look for further explanation. So this concept of elementarity is not a rigorous concept, so I'm not going to attempt to give a rigorous definition, but just as an example, for example, electron, for what we currently know, it's an elementary particle. It does not have any more microscopic explanation or description. And so this quest for more and more elementary constituents, this reductionism quest, it led to the construction over 20th century of the standard model of particle physics. So there's this table of 17 elementary particles. There are some features of this table that some people might find a bit unusual. For example, these particles, even though we consider them elementary, many of them are actually unstable, so they decay. But in spite of that, they're sufficiently long-lived, so we can observe them and we conclude them that they exist. Another feature of this table that we will contrast with later Bootstrap scheme is that this table is not, we don't conceive it nowadays as inevitable. It's a bit of a piecemeal table, meaning that some of these particles who are in this table, we don't actually, like, if you were to remove them from the table, the theory would still make sense. Like, for example, there are like muon and muon neutrino. We could just like remove it and the theory would still be okay. It would be a slightly different world, but it would still be consistent. Or there are some interactions, like there are weak interactions, strong interactions, electromagnetic interactions. We could remove, say, strong interactions. Okay, it would be a very different world, but it would still make sense, I mean, mathematically. So we kind of play a Lego game. We can put these things together, a little bit at will. Okay, that's the world it is, but we don't really know why it is the way it is. And from these elementary particles that I showed, you can build many composite particles. You don't see this table very well, but that's precisely the point. There are hundreds and hundreds of particles that are, cataloged by dedicated people, particle data group collaboration, and well, you don't need to know them because they are all built out of elementary particles. So this begs the question: why is it, even though we tacitly assume that that's the way it should be, but why is it that we can always reduce all the particles to a collection of these elementary building blocks? Okay, that's not maybe a well-posed question, and a better question would be, can you imagine a world which would be somehow operating according to different rules? So that's the question that I would like to think about with you. So, well, elementary particles in the standard model, they have 7 properties. They are point-like, and they have interactions which are very feeble, very weak. So this second property is very important because it allows us to kind of separate the system and say, okay, this system is made out of a few particles, and we can separate them into components. But if the particles are strongly interacting, then you cannot even cleanly separate them, and then it would, the whole concept of composed and elementary particle would make a little sense. So that's why it's important. And for example, let's take the proton. So the proton, it shows that this qualification, at least in some regime, weakly interaction, is important. Because the proton usually, okay, if you read about proton in science popularization books, you say, well, the proton is made out of 3 quarks. Well, let me tell you something that popularization books don't always tell you, is that, in fact, this is a bit more complicated than that. So if you just take a proton at rest, or as we say, at low energies, then in fact proton is not just made of 3 quarks, but it contains a soup of other particles, gluons, and quark-antiquark pairs, virtual quark-antiquark pairs, which pop out of the vacuum and they go back to the vacuum. So given that there is a strongly interacting soup, you cannot even say that all of these soup constituents are elementary particles because they're strongly interacting. But here, it turns out that when you go to high energies, if you smash the proton with a photon, which has, for example, with a photon which has a very high energy, then this photon will will pick out of this soup constituents of the proton, and those constituents will behave weakly interacting. And so this is what allows us to say.
Weakly compared to the energy applied or compared to the energy of the statue?
Well, no, the strength of interaction is a number. It's a dimensionless number.
Weak or strong? What do you mean here?
Like, for example, the strength of interaction, it's a number, so it's going to be 0.1.
No, absolutely large or relative to another one?
Relative,
Relative
it's small relative to 1.
Okay.
Yeah. So this phenomenon called asymptotic freedom is very important in order to be able to say that quarks exist as elementary particles. So it provides a sort of boundary condition for definition of the whole theory. But now, coming back to my question, could we imagine a different world in which a proton would not have any elementary weakly interacting constituents whatsoever? So if in such a world, we would say that, okay, it would be anti-reductionist world. So could such a world exist? Okay, it's kind of a weird question given that we already know that our world is not like that. But if we roll back the history clock to the 60s, when these particles, this huge number of particles that we now know are composite, were starting to be discovered, then actually this idea, it was one of the dominant ideas in theoretical thinking. So it's usually associated with the name of Geoffrey Chew, who was a theoretical particle physicist in Berkeley, who around 1960, when these particles started multiplying like rabbits, he proposed this idea which he called nuclear democracy. So he said that could we imagine that all of these particles that there's so many that we don't know how to classify them, that they're all equally fundamental or equally composite. We should not try to reduce composite to fundamental, but just let them view them together as equally fundamental. So this is a bit of an outrageous idea because you can say, well, in physics we build theories, and theories are mathematical theories. So, but these are just words. How do you start even from writing some equations from which you're going to compute some things? This is just visual thinking. And so he did propose actually a theory. He tried to propose a theory, and that theory was based on the principle of self-consistency. So in traditional theory, if we see two particles like particle A and particle B, we say, well, it's because like particle B is probably made out of A, or maybe both B and A are made of some other particles that we haven't yet discovered. But in Chew's theory, if you see particle A and particle B, it's because A couldn't exist without B, B couldn't exist without A. That's the way it is. And so he tried to formulate some axioms. These were pretty reasonable axioms, like they were based on, most of these axioms, they were based on things like consistency with Lorentz invariance and consistency with quantum mechanics, like probabilities should add up to 1. Okay, he tried to put some extra assumptions, and he called this whole self-consistency scheme Bootstrap. So he was referring to like trying to lift yourself by your shoelaces, and so it's magic. So the whole thing, if it works, it's kind of magic. And nowadays, this word bootstrap, it's like one of the most abused words in physics, and you can either love it or hate it, but usually it refers to getting something out of nothing. if it's possible. And in physics, it's really weird. But in mathematics, it's actually not so weird, because there are many, many objects in mathematics which you could say work analogously. And this is perhaps the simplest of them. If you take all the prime numbers, there are infinitely many prime numbers. They're all equally fundamental. And they do not come piecemeal. You cannot easily imagine a sensible theory in which you throw out some of these prime numbers or just take a few of them. It's clearly going to be not the full thing. You can give other examples. If you take, I don't know, for people who know about Lie algebras, you cannot just take a theory in which you take 3 generators of the Lie algebra and throw out the rest of the generators. That's just, all generators of a Lie algebra talk to each other, and they are all equally fundamental. So that's the kind of thing that he was trying to imagine if it can be realized in physics. And this theory of Chew, it was not just words. It actually scored some early successes, better than any other theory in the 60s. For example, it was the first theory that could predict the mass of the rho meson. So the rho meson was one of these particles that were being discovered in those days. And when it was discovered, the way Bootstrap explained the rho meson was in the following way. So they said, well, the simplest actually hadron particle is the p meson. And you can try to imagine that p mesons, they interact, they get attracted to each other by exchanging rho mesons. And okay, there is some interaction strength, which I called here G, and then okay, this diagram means that the rho meson is exchanged, the coupling interaction strength. And so there are these p mesons which interact via the rho meson, by exchanging the rho meson. And so when there are two particles, like two p mesons, which get attracted, then they can form a bound state. So now we have already p meson, rho meson, and the bound state. And so what is this bound state? Well, then you say, but perhaps this bound state is precisely the rho meson itself. So now you start seeing there is some self-consistency going on. So the rho meson plays simultaneously two roles. It's the particle which mediates the interaction, but at the same time, it's the particle which comes out as the result of mediating interaction. And if you take this assumption, then it gives you an equation for the coupling and for the mass of the rho meson. And people solved this equation. They got the number which was in reasonable agreement with experiment for those standards. So that's the way it worked. And for 10 years, this scheme, this Bootstrap scheme, was actually intellectually dominating the field. And for those who know, when Gell-Mann wrote a paper about quarks, in which he proposed quarks, he actually felt compelled to notice that my theory of quarks does not contradict the Bootstrap. Because if he didn't say that, then people would dismiss his theory of quarks right away. So it was not a joke. But eventually, this nuclear democracy was forgotten, because after 10 years, it was understood that actually elementary constituents exist. So the quarks were proposed, then they were discovered, experimentally observed around 1970. And so the microscopic approach, the reductionist approach, won. The world was more boring than Chew imagined it. And well, of course, the experiment spoke. That's the ultimate truth. But philosophically, I think it's an important lesson, because, well, it showed kind of that the world didn't have to be necessarily the way it is. And the moment this idea gets out, the idea of the Bootstrap got out of into the intellectual space. Any good idea is right in some sense. And perhaps it didn't work in particle physics, but perhaps it can work somewhere else. And that's going to be precisely the second part of my talk. So I will show that this Bootstrap idea actually does work in a very different parts of physics, in a part of condensed matter physics, which is concerned with continuous phase transitions or critical points. So I'm switching the gear quite severely. So I'm going to talk about thermodynamics, about phase transitions. I have to remind you what are these phase transitions. And the phase transitions that most of you are familiar with are so-called discontinuous phase transitions. So when you take a block of ice and you melt it, or if you take water in the kitchen and you boil it, these are discontinuous phase transitions because the two states of the substance which get transformed into each other, water and ice, or water and vapor, they are radically different from each other. But there are different phase transitions which are, in a sense, more beautiful, more universal, and they're called continuous phase transitions. So let me explain you where you can find them in real life or in the lab. So here, in the first part of the slide, I have the phase diagram of water, which means that for every temperature and pressure, I tell you in which state the water is, like it can be in the liquid, solid, or gas state. But there is this interesting point on this phase diagram where the distinction between liquid and gas seems to disappear. So in fact, if you go around this critical point and you connect gas to liquid, liquid to gas without crossing any lines, these lines are the lines of discontinuous phase transitions. So the distinction here between liquid and gas disappears because at this point, the density of liquid becomes equal to the density of gas. So this point is precisely an example of the critical point to which this bootstrap theory is going to apply. Another example of this continuous phase transition you can find in the theory of magnets, or if you know, there's this three-dimensional Ising model which describes it mathematically. So if you take a magnet, here, for liquids, the two parameters were temperature and pressure. For magnets, the two parameters that you can vary are the temperature and the magnetic field that you apply to the magnet. And now, depending on the temperature, if you apply a magnetic field, a very small magnetic field, it may be sufficient for the magnet to order in some direction. So that's what we call a spontaneous magnetization, which can point, you can order the magnet by applying magnetic field, but when you remove the magnetic field, this magnetization remains, and it can be either positive or negative. But as you now start heating up your magnet, and you don't have to typically heat it up too much. I mean, if you have a magnet on your fridge, it's enough to use a lighter. Then at some temperature, this magnetization is going to disappear. So the magnet will stop being a magnet. And so this temperature where the magnetization disappears is also an example of the critical point. So you see the analogous quantity to the difference between the densities of the liquid and gas. Here, it's the magnetization which goes to zero at the critical point. So these are the critical points of continuous phase transitions, and this is going to be our interest. So the main characteristic property of these critical points is the presence of fluctuations. So presence of fluctuations at all distance scales. So what does this mean? If you, so here I'm showing 3 snapshots of a simulation of a magnet at the critical temperature, and the dark and the white spots, they correspond to the microscopic magnetization pointing up and down.
What scale actually in these pictures?
The scale, so the smallest point that you see, it's 1 lattice spacing, the interatomic distance.
Is how it obtained by X-ray crystallography, or how you get to the result?
It's a computer experiment.
It's computer experiment.
Yeah, simulation.
I don't know what it is.
Yeah. It's a computer experiment, but you can check this by scattering neutrons on real magnets, and you can verify this picture. So we think it's true. So what I wanted to point out is that there are these islands, there are these dark islands in the sea of white, and you see that the sizes of these islands are, there are islands of all sizes. So this is only true if you do the simulation at the critical temperature. If you do the simulation at the temperature which is non-critical, then you will see islands of characteristic size. But here you see islands of all sizes, and that's what we mean by fluctuations, because these islands, they, as you go ahead, they flip. What becomes white becomes what was white becomes black, and so on, and it happens at all distances. So this absence of characteristic scale, that the fact that there are these islands of all sizes, mathematically we express it by saying that our system has scale invariance. And in fact, it also has conformal invariance, but I will not have time to define it rigorously mathematically, but okay, I'll say some words about it later on.
Dimension 3?
In dimension 2 and dimension 3, it's true both in 2 and 3 dimensions. Yeah. So this was for magnets. But now let's go to liquids. And let's see what liquid behaves like near the critical point. There's something interesting here that you can actually see now with your naked eye, not just in a simulation. And there are some nice YouTube videos that I invite you to see. So what you basically notice is you approach the critical point in the liquid by varying temperature or pressure. Then you start seeing, so the liquid initially is transparent, like water is transparent. But here you start seeing some weird clouds like all around your volume. And then precisely at the critical point, the whole liquid becomes white, like milk. So why does this happen? Well, this happens because light scatters on the fluctuations and propagates in all directions, and that's why it doesn't get to you. And the fact that it doesn't get to you, it means that you cannot see through. So you see this milky substance. And the fact that light scatters on fluctuations, moreover, for light to scatter on the fluctuations, they have to have a sufficiently large size for the light to scatter on them. And the wavelength of the light is several hundred nanometers. And the typical interatomic distance is an angstrom. So 1,000 times smaller. And so it means that there are fluctuations which have size of thousands of interatomic distances. And this is very, very weird, because in a typical substance that you take, which is far away from critical temperature, the fluctuations, of course, there's always some fluctuations. It's thermodynamics. But typical fluctuations, they have the size of interatomic distance, like 1, 2, 3 interatomic distances. And here, thousands. And actually, we believe that the critical point all the way to infinity. So this phenomenon called critical opalescence, you can look it up. Beautiful phenomenon. So a little bit of mathematics. So mathematically, we describe this presence of fluctuations through correlation functions. So we look at the fluctuating quantity. For example, the deviation of density from equilibrium, which is something that I call here delta rho. So rho is the equilibrium density, delta rho is the fluctuation, which can go positive or negative. And then you take this delta rho and you average it, which is what I show by these brackets. You can average either over time, or you can consider all possible configurations of your system at thermal equilibrium, so-called thermal ensemble. And you can average over this ensemble. There's some ergodicity hypothesis these two averages are the same. And okay, if you just look at one point and you look at this deviation from average density, then by definition this average is going to be 0. Nothing interesting is happening. But if you look already at 2 points, this 2-point correlation function, delta rho at rho 1, delta rho of rho 2, then it's going to be non-zero. Because if if you look at one point and, for example, delta rho is positive, there is some overdensity at one point, then it's more probable that at a nearby point, this overdensity will survive. So this correlation function, you expect it to be positive on general grounds. And if the system has a scale invariance, which is true at the critical point, this correlation function mathematically will have a power law form. So it's going to be some constant over distance between the 2 points, ρ1 minus ρ2, raised to some power. And traditionally we call it 2 delta, this power, and delta is some numerical parameter. So this formula has to be true as long as you go to distances r1 minus r2 larger than interatomic distance of your material. And so this parameter delta, which I just introduced, it's an extremely interesting parameter. It's called critical exponent. We don't know its exact value most of the time, but we can make experiments. We can measure it experimentally by scattering, say, neutrons on our or light on our material, and we can also make theoretical predictions for it. And in the case of liquids, we know this exponent, and it's with a few digits, like, okay, with the 6, 7 digits. Here's experimental value, 0.51814889. And we'd love to know more digits, but that's, you know, you take what you can. And the amazing thing, the reason why I would like to know more digits about this exponent is that it's a universal number. So by universality, I mean that if you take two different liquids, you put them at their corresponding critical points. Of course, for each liquid, the critical point will have a different temperature, different pressure. But this number delta is going to be the same for all liquids. We think that that's pretty amazing. So this universality. It's an experimental fact, and I'll tell you how it's explained theoretically. But moreover, this exponent turns out to be the same not only for liquids, but also for magnets. So for magnets, the fluctuating quantity is the magnetization, local magnetization at the points R1 and R2. You take this correlation function at 2 points, you find the power law, and amazingly, the number delta that you get for magnets is the same as you have for liquids. So this was first observed experimentally. So what this means is that critical point of water or of any liquid is the same in a certain sense as the critical point of a uniaxial magnet. And so how can it be that there are two things which come from two different physical systems and they end up to be the same? There can be only one explanation if there is some rigid mathematical structure which describes these critical points. So we have to look for the structure. And this structure is called conformal field theory. And I'm going to say some words about it as we proceed. So this is the structure behind this critical universality. But where's this bootstrap? So I was promising you infinitely many fundamental constituents, lack of reductionism, nothing can exist against everything else. And so far, I just give you one number, delta. But actually, there is not just one number, delta, but there are infinitely many numbers, delta I, delta 1, delta 2, delta 3. And to see these numbers, you just have to make a slightly more precise experiment. So you still look at this two-point correlation function of density-density fluctuations. But now you measure it more precisely, and you will see that, in fact, it's not exactly a power law. Of course, it's not going to be exactly a power law. There are going to be some deviations of this power law. So there's going to be some infinite sum of power laws. So there's going to be 1 power plus another power, larger power. So it's going to be like a power series expansion in the inverse distances, except that the powers are going to be non-integer numbers. They're going to be these numbers delta 1, delta 2, delta 3. which are some non-integer numbers. And we know some of these numbers, so here I give you some table for these numbers. You see there are complicated numbers, which are increasing in magnitude. And all of these numbers are equally universal. So not just the first of them, but all of these numbers are critical exponents, and all of them are equally fundamental.
But the constants are not universal.
The constants are not universal. You're completely right. These constants are not universal. There are going to be some later on constants which are universal. I'm coming to that. So what are these numbers? How should we think about them? Well, one way to think about them is that these are some sort of eigenfrequencies corresponding to sort of eigenfluctuations. So I told you that I'm looking at these fluctuations of density, but density is just one fluctuating quantity, and what this equation is hinting at is that there are infinitely many types of fluctuations which coexist in the system, and each of them is characterized by this parameter delta, corresponding parameter delta 1, delta 2, delta 3. And the fluctuation of density, which physically seems to be a natural thing to look at, turns out that mathematically it's not, because it's not itself an eigenfluctuation, it's just an infinite linear combination of different eigenfluctuations which exist. It's just an experimentally convenient thing to look at, but mathematically not. And when you do this decomposition, it's like a linear algebra, you discover this infinite sum with different powers. So that's what this expansion is telling us. And so we have two strategies to compute these numbers. Actually, I mean, before even the Bootstrap strategy, there was a more traditional strategy that was trying to look at all of these different fluctuation types and identify some of them as fundamental and others somehow reduced to the fundamental ones. And this strategy, it works to some extent, but then it kind of ran out of steam a little bit. And the reason why it did so, because remember I was telling you that it was very important that elementary constituents of your system, if you would like to think in terms of elementary constituents, they have to be weakly interacting. And it turns out that in this system, this condition is not satisfied. So if you try to separate everything into elementary fluctuations, it's not going to work because these elementary fluctuations strongly interact with each other. And so then we propose this bootstrap scheme, which treats all fluctuations on an equal footing as equally fundamental. And you try to write down consistency equations that will just tell you that one fluctuation type cannot exist without other fluctuation type. And these equations follow from conformal field theory. So this is what I told you. There are infinitely many fluctuation types, infinitely many superimposed fluctuating layers in our magnet, in our liquid, and we have to find these layers. So if you know some elastic mechanics, then you can find useful this analogy of oscillations, fluctuations in critical point with oscillations of an elastic body. For example, an airplane, fluctuations of an airplane, oscillations of an airplane, they can be decomposed in different eigen oscillation types, eigen modes, which I show this here. My dad is an aircraft engineer, so I asked him to make these pictures. But there is actually some difference between airplanes and magnets. Let me first tell you the similarity, and this concerns the orthogonality of fluctuations. So I told you, so now here I'm going to give you some math again. So there are different fluctuation types, and I call them here A1 of x, A2 of x, A3 of x, infinitely many. And what I mean by orthogonality is that if I consider a two-point function of these fluctuations ai of x and aj of y, then this is going to be a power law 1 over x minus y to the 2 delta I if I is equal to j. And it's going to be 0 if I is not equal to j. And this, if you remember linear algebra, it's similar to orthogonality of eigenvectors of a symmetric matrix, this property. So actually, one nice thing about this, to think about this two-point function, is to think kind of of it as a hitting experiment. You take your system, you hit it at the point x with a hammer, and this creates some disturbance in the system, and then at the point y, you read off what is happening with some experimental apparatus, and the result of this reading off is precisely this two-point correlation function. That's just another way to think about this quantity. But now, what's not like for the airplanes is a very important nonlinearity effect. So fluctuations of the airplane, they are, for all practical purposes, they are linear. You can do linear theory for them, but here not. And this nonlinearity is expressed through the existence of three-point correlation functions. You take three fluctuating quantities, a1 of x, a2 of y, a3 of z, and you consider three-point correlation function. And so what it means in terms of this hitting experiment is that, okay, you take two hammers and you hit at your system at points a1 of x, a2 of y, and then it turns out that you will have some non-trivial read-off of a fluctuation of a third kind at the point z, a3 of z. And so you see that two fluctuations of two different types, a1 of x and a2 of y, when they propagate from points x and y to z, they can transform into fluctuation of this type 3. And for the airplanes, that would not be the case. If you just take an airplane and if you excite two fluctuation modes, mode 1 and mode 2, the airplane will just keep fluctuating, keep oscillating in those two modes. And it's going to be extremely small nonlinearity, which will generate other modes. And so in our theory, this probability of fluctuations to be transformed from types 1 and 2 to type 3 is going to be parameterized by this constant. Okay, there is some dependence on x, y, z that I'm not writing, but there is some overall constant, which I call here lambda 1 to 3. And unlike these other constants that I was mentioning before, these constants are also universal and non-zero, and order 1 numbers, unlike for small nonlinearities. And so we are getting pretty close to the punchline. So how do we do the bootstrap? Well, the bootstrap corresponds to the 4-point hitting experiment. We consider, and then it stops. You don't have to consider high point hitting experiments. That's the nice thing about the whole thing. So you consider 4 points, 4 fluctuations, a1, a2, a3, a4. So you hit your system at points a1 and a2, or at points x1 and x2. You read off what is the signal at points x3 and x4 for fluctuations of type a3 and a4. And so the result of this experiment, it can be described by fluctuations ay, a2. You can expand the result of generating these fluctuations a1 and a2 into a basis of fluctuations of type ak, which is this red line here. And this expansion is going to involve these coefficients lambda 1 to k. These fluctuations ak propagate. We assume that we have a full list of fluctuations of our system, and then they get again transformed and read off at points x3 and x4 with this other coefficient lambda 3, 4k. So that's the experiment that I would like to do. And this experiment, it measures this 4-point correlation function, a1, a2, a3, a4. AK is the full basis of fluctuations that I have to fix from the self-consistency.
Okay, and
K is an integer. It runs from 1 to infinity.
It's a finite integer.
Well, it's a finite integer. Yeah, it runs over integers. There's a sum over K that I haven't written. So what's special about this 4-point heating experiment? It's because I can perform it in 2 different ways. I can heat the system at points A1 and A2 and read off A3 and A4, or I can heat it at points A1 and A3, or X1 and X3, and read off an A2 and A4. And both experiments, they describe the same correlation functions, so the results of this experiment should agree. But you see that the computation that I do is not the same, because on the left-hand side, the computation involves these coefficients lambda 1 to k and lambda 3 for k. And on the right-hand side, it involves different coefficients, generally different coefficients, lambda 1, 3k and lambda 2, 4k. And also the points are not the same, because everything is happening in space, and there are points x1, x2, x3, x4, which are not the same. So these 2 expansions, they do not manifestly agree, but they should agree. And that's what we call the Bootstrap constraint. This is the self-consistency constraint that we would like to use. So if you have not seen, you probably have seen this constraint in a slightly different form, if you have ever heard anything about string theory. So in string theory, we don't do heating experiments, but we don't compute correlation functions depending on x, but we compute scattering amplitudes. And these scattering amplitudes are computed by considering surfaces which join like some pans coming from infinity. And if you take a surface with 4 holes, like here on the left-hand side, and then you deform it so that the joining tube is horizontal or vertical, like here, then since it's the same surface that you're considering, you're modifying the geometry, but it's the same topology. So the equations of string theory, they guarantee that the result is going to agree. And so string theory scattering amplitudes, they actually satisfy the same sort of equations that I'm writing down. And okay, string theory is a very particular theory. It's also a rigid theory, and you can also interpret what I'm saying by thinking that we are saying that what string theory is trying to apply to quantum gravity, we are saying, in fact, it applies to much more mundane, experimentally, easily verifiable systems like magnets. But let me give you some more math, if you can handle it. So mathematically, what this means that I'm doing, I'm studying a particular family of associative commutative algebras where objects that I'm multiplying are labeled by points of Euclidean space, x. And so this is my equation that, so an algebra means that you take product and you express it as a sum of basis elements of the algebra. So this ai of x, a j of y are basis elements. I'm multiplying them, and there are some structure constants of the algebra, lambda ijk. There are some coefficients, which are just some fixed functions of x, y, z. And there's the same basis ak of z appearing on the right-hand side. And you might think that these algebras are not particularly constraining, but what makes them constraining is that this equation has to be invariant under conformal transformations. I already mentioned conformal invariance before very briefly, and what I will just say that if you have ever seen Escher drawings, where like everything is deformed, but it's deformed in a way that all angles they remain the same. So lines which are perpendicular, they remain perpendicular. Like for example, if you look at this point here, but the scale can change locally. So this is the definition of conformal transformations. And these equations is indeed not very restrictive unless you impose this assumption of conformal invariance. And once you depose it, then this becomes conformal bootstrap. So what can we do with this? I'll just give you one example how we can take an experimental system and study it using the conformal bootstrap, and what is it that we can do. So this is a very famous phase transition. It's called superfluid transition in liquid helium. So helium is a very interesting liquid. It's the only liquid that does not freeze even at 0 degrees Kelvin. But it goes to the superfluid state at a temperature of a few Kelvin. And if you look at the system precisely at this superfluid transition temperature, then that's where this critical point lies. And various quantities of physical interest, they show singularities near this point. Like, for example, one quantity that people like to study is the specific heat, which means like how much heat you should put into the system to heat up the helium by 1 degree Kelvin. This is called specific heat. And it turns out that as you approach this critical point, this specific heat diverges. So why does it diverge? Because it's these fluctuations. There are lots of fluctuations in the system, and when you heat up, you have to heat up all of these fluctuations, and you need a lot of heat in order to do this. So this is this curve, this divergent specific heat. Excuse me. So people can study this curve very, very precisely. Liquid helium is a very pure system, but unfortunately, if you're like really ambitious, if you want to study this, you have to do it in space, because if you do it on Earth there is gravity, and gravity kind of smears out this peak, so you have to put your experiment on a space shuttle or something like that, on a space station. And some people at Stanford did it, and they measured the power law with which this specific heat explodes very, very precisely. And actually, it's this number alpha. And from this number alpha, you can measure you can extract one of these numbers delta that I was talking about. Just one. So there are infinitely many deltas, but one of them you can extract out of alpha. It's called delta epsilon. And there is a certain experimental prediction for this. Okay, I can say more about it if you're interested. And the trouble is that there is not a very good agreement between theory and experiment. So this is a famous system, so many people have studied it. And here in red, you can see like different experimental measurements by the same group. And okay, first they measured some number, okay, then they measured slightly smaller number. Eventually they got to at least agree with the first experiment, and that's the final measurement that they did using the space shuttle. And then, okay, there are some theoretical groups that, of course, they do this. They compute the same thing theoretically, and some of them are not very scrupulous. Like every time experimentalists find a number, they magically find exactly the same number. Then the experimental result change. They also change. Then the experimenter goes back. They again update their theoretical prediction. So then there are other groups which like kind of stay constant, but there is a big disagreement. There's a big disagreement between theory and experiment. And in physics, we count disagreement in standard deviations. And for example, when Higgs boson was discovered, it means that the hypothesis of absence of Higgs boson was excluded at 5 standard deviations. That's kind of the gold standard of discovery. So here the discrepancy is 8 standard deviations. So it basically means like total crisis. No. So but of one group, but the other group, it's like a perfect agreement with the experiment. So what do you do? Who is right? Who is wrong? So one nice thing about Bootstrap is that it can, if it says something, it's a final verdict. There's no appeal, because the Bootstrap calculations, like even in physics, often that even theoretical calculations, they have some uncertainties which are not fully under control. So So it's kind of dark, a bit something which people hide under the rug. So the nice thing about the Bootstrap is that it's a totally mathematically rigorous method. So everything is you don't have to manipulate any divergent series or which we often have to do in physics. Like everything is completely kosher, and so when we improve our, if one Bootstrap group obtains some result and then another one obtains the result, the error bars can only shrink. The result cannot jump. So the results are rigorous. And so actually, I'm happy to announce that this puzzle has been resolved. Unfortunately, not in the way that I wanted it to be resolved. And this is going to be reported in a talk by my collaborator, David Simmons-Duffin, in the workshop that we are going to have tomorrow and the day after tomorrow. Simon's collaboration on the non-perturbative Bootstrap is going to have a yearly meeting, and that's going to be one of the highlights of this meeting. So that's the kind of things that we can do. And okay, this is just one example, but we have resolved many this kind of wishy-washy puzzles like that and pronounced final verdicts on experimental results. So that's the Bootstrap at work. We have infinitely many fluctuations, we impose consistency conditions, and we make experimentally verifiable predictions. So it's kind of nice that these ideas of Geoffrey Chew, who unfortunately died a couple of years ago, they found second life in condensed matter physics, even though they didn't work in particle physics. So this shows that every good idea is true in some extent, and it shows the great unity of physics. And it also shows something that my PhD advisor and an early messiah of Bootstrap, Alexander Polyakov, said in his book, that the garbage of the past often becomes the treasure of the present and vice versa. I'll stop here.